So we have the following example again on the inductors chapter. So anytime you're solving a question like this to do with the magnetic flux, the main idea behind this entire chapter itself is that you have a external magnetic field from something else, some other object. That magnetic field is going to induce or cause a current in a loop. So this is a loop. So that's the context behind such questions, whether you have something like this or something else where you just have a fixed loop like this. It doesn't really matter. Now in the question we're being told that we have a radius here for this semicircular shape, which is 40 centimeters. I'll say that's 0.40 meters. So it's good to convert to standard units. We also have a angular velocity, 8 revolutions per second. I'll explain to you where this angular velocity came from a bit later. We have a magnetic field that is constant. It's pointing into your screen. And it's 3 Tesla, and we have a resistor with a resistance of 10 ohms, and we're being told to find the EMF and the current. So the first thing to work on here is to keep in mind that these types of questions will always involve the following 3 formulas. Majority of the time it's the following 3 formulas: the magnetic flux formula, the EMF formula, and the Ohm's law. So as you know, we're going to find the current from Ohm's law, and then we're going to find the EMF from the following equation using this guy. That's a quick summary of what we're going to do. Now there's something we have to pay attention to in this question. Our angular velocity is being applied here, and this area that's been grayed out is the area that's actually turning. That's what the grayed out area means, meaning that the rest of this loop is not turning at all. It's in the same spot. So when you turn this thing, it's only this area that keeps turning. Now this tells us that the angle between the normal vector, again the normal vector is, or the area vector is the same thing, it's always perpendicular to the surface. So in this scenario, for this moment in time, I'll assume that my circuit, the piece of the circuit that I've circled is on the XY plane. It's not moving yet. And with the normal vector, you can always remember that it can either be pointing with the magnetic field or away from it, assuming that both of them are sort of perpendicular to the surface of the actual loop. Now, I'll assume that my normal vector is pointing with the external magnetic field. So I'll put an X. So what that means is that the angle, in this moment, the angle between the magnetic field and a normal vector is 0 degrees. Now the thing to keep in mind is that when this piece keeps turning and turning, the angle between the normal vector and the magnetic field vector will change. Basically, it's the normal vector that's always moving either away or towards the magnetic field. The magnetic field is fixed on the negative Z position. negative k hat position. It's always into your tablet. The magnetic field never changes direction. It's always the normal vector that's changing direction from it. So hence the angle between the normal vector and the magnetic field keep changing as we turn this loop. So basically what we're saying is that what's changing is this angle in the magnetic flux. Now for the rest of the loop, it's not really changing at all. Nothing changes in the rest of the loop because it's not turning. So your angle isn't changing, and the magnetic field is always constant. And the area vector, or the normal vector, is also always constant. It's not changing. So hence that's why we're not really paying attention to this part of the loop. We sort of ignore it. We need to focus more on, because of the context of the problem, more on what's actually important, which is what's happening here. Now, I'll kind of start solving the problem. So we know that the angle between the normal vector, or the area vector, it's the same thing, is changing. This is our equation. Whenever we hear the word change, like I said, the angle between the two vectors, the area vector and the magnetic field vector, is changing. The moment you hear the word change, you already know it's a derivative, a rate of change. With respect to time, the angle is changing. Hence our angular velocity. So the angle changes at a velocity. That's what the angular velocity is. Now we take the derivative of the following equation, and we already know what's changing and what's constant. The area and the magnetic field are constant, and it's just the angle between these guys that is changing. So that's the only thing we can actually take the derivative of. Now the derivative of cos is sine minus sine, actually. It's minus sine theta. Now there is one thing I forgot to do. I had to actually change the angle. I want to describe this angle between the normal vector, or the area vector, and the magnetic field. This angle, I want to describe it as a arc. So theta would be equal to the angular velocity times time. Because revolutions per second times second, we can get rid of the seconds, and then we just have revolutions, which we convert to radians. So one revolution would be 2 pi radians, and we would get the angle theta in radians. I wouldn't know how to explain that to you more precisely, so I would suggest asking a teacher, but it's just the idea that you have a circle and you have a specific angle, but you don't want the angle, you want this length, the arc length, instead. So to get the arc length, we use this formula here to describe the angle theta. So you angular velocity times time, and then we convert to radians as well. So yeah, this is the thing that I forgot to do. So I should have first used the arc length formula and substituted it in here for the angle. So it'd be WT. Forget about the pi rad for now. We can convert the units later as well. It's not a problem. It's just to get the right, to take the right derivative to get the right answer. So we would definitely get, we would still get negative sine WT. But remember that we have to use the chain rule now. We took the derivative of the outer function. Now we're taking the derivative of what's inside that function. So basically the derivative of w times t, and we know that W is always constant, 8 revolutions per second, so derivative of t is going to be 1, derivative of variable is 1, so we're just going to get W minus WAB sine of WT. So that's the chain rule for you for derivatives. So that's awesome. We got this equation, and now we're going to simply find the electromotive force, which is easy again. The formula is the same thing, except that you have the n there. The n is the number of turns the circuit has. In this scenario, the circuit only has one turn. The question hasn't mentioned the number of turns, so we just assume the number of turns is 1. So that n represents the number of turns. So it's minus 1. The general formula, actually, I want to show it to you first because it might be useful for you for these kinds of questions, is minus n a b w sine of wt. That's the general formula. In the context of the fact that you're turning something and that the angle between the area vector and the magnetic field vector is changing. So that's minus 1, and now I think I'll start plugging things in. The area is going to be pi r squared. Or pi a squared in this scenario, which is pi times 0.40 meters squared times the magnetic field, which was 3 Tesla, times the angular velocity, 8 revolutions per second. So again, we have to convert to radians, don't forget that. That's the standard SI unit. 2 pi radians is 1 revolution. Now I'm just gonna write the sine as sine of WT. And why? Because the thing is that the electromotive force is also changing. It's not constant. If they'd given me a specific point in time, I could have plugged it in there, and then I would have also plugged in the actual angular velocity. But in this case I didn't, because I know that the EMF is also changing as the loop keeps turning. So because of that, I leave it as sine of WT. I mean, I can still plug in 0.08 revolutions per second, but nothing's going to happen inside the expression. So I'll just leave it as WT. If your teacher asks you to write the actual value, you can go ahead, but nothing's really going to change inside unless they ask you for a specific time at which to find the EMF. I'll plug this in my calculator. So I get negative 75.8 sine of WT. I rounded that up. Now, one thing I've realized, we've probably realized here already, is that well, two things. The first thing is that I just wanted to remind you that what I showed here was just an example. I assumed that, we weren't turning anything. So the actual angle between the normal vector and the magnetic field vector keeps changing. It's not the same. Okay, that's just a quick reminder in case I forgot to explain it earlier. The second thing is, now we know that the EMF, the electromotive force, or the voltage, is changing constantly. So what that tells us is that the current is also changing constantly. We're not going to be able to find a fixed value, a fixed number for the current. It won't be like 5 amperes. It's probably going to be something like 5 times sine of WT or something. So now I'll have to erase a few things. So we know that voltage is equal to I times R. We'll rearrange for the current because that's what we have to find. Now voltage was negative 75.8 sine of WT. And we divide that by the resistance, which is 10 ohms. So we get a current that is negative 7.58 times sine of WT. If I'm not wrong, this is very similar to waves optics in modern physics, that class, in the sense that it's a similar function to what you would see for I believe it was photons or light, or I actually forgot what it was. There was a chapter. What I just highlighted here is likely the amplitude, the highest possible value the current would take. So the highest possible value would be 7.58 amperes, but again, it keeps changing according to time and according to our angular velocity, so it's not exactly the same. So this is like the closest we can get to a possible answer in this question. If they asked for a specific moment in time to find the current for, then yeah, we could go and find the actual number, a fixed value for that moment in time. The other thing I wanted to explain was why, for example, for the area we only found the area of the semicircle and not, let's say, for these two pieces. So now one of the mistakes I made in this question is that we're dealing with a semicircle. I used the equation for the area of a circle, which is pi r squared. I was supposed to divide it by 2. Now it's not a problem, because all I have to do is I have to take this answer and divide both of these guys by 2, and I'll get the same answer. Because if I go back to the previous equation, we're just doing multiplications and divisions, and it's not really an issue how we necessarily do them, as long as they're done in some order. So you see this term there, I should have had a divide by 2 on it as well. So you'd have something like this. So in this scenario, the best quick fix, let's say you're solving this problem in an exam, is to just divide the final answer by 2 and just leave a note like, yeah, I forgot to put a 2. Or just put a 2 if you have some space underneath. It's not going to take that long. So when I divide negative 75.8 by 2, I get negative 37.9. I've also now made another mistake that I just realized, and I will explain that to you. Give me a second. So again, I divided this guy by 2 and I got negative 30.79. This is in amperes and this is in volts. It's a negative sign. I'm not supposed to have a negative sign in any of these. And why? Because before, when I took the derivative of cosine theta, it gives me negative sine theta. And then on top of that, so basically this part of this massive equation, specifically this part, would already have a negative sign on it. And on top of that, this massive equation has its own negative sign. by definition. So those two negative signs, this one and this one, would cancel each other. And because of that, I would no longer have a negative sign. It would be a positive sign. They would cancel each other out. I hope this helps, and please watch these videos on 2x speed. Take care and have a good day.